So then it was getting the wrong answer for soft gluon emissions, but it just put a cut on angles. And that roughly simulated the coherence effect. That was old Pythia from up to 1995 or something like that. New Pythia has a better method that I'll tell you about in a moment. But I should first tell you about something called the leading color approximation that's used in these parton showers. Theory is SU3 color gauge theory. However, that's very inconvenient to deal with. So what people use is they keep track of the color of the shower, but they treat it approximately. So instead of saying a gluon is carrying the color 8 representation of SU3, they pretend that the gluon is carrying color 3 times color 3 bar. Now, in group theory, 3 times 3 bar is 8 plus 1. And they get rid of the 1. They just keep going. If you do it that way, then you can say, here's a gluon, here's a quark went to a gluon. So the quark has color 3, the color 3 goes along with the gluon. The gluon has a color 3 bar, which connects back to the color 3 of this other daughter quark. So you just draw lines like I drew. Those are color 3 or color 3 bar color lines, just to tell you how the colors form. And your program keeps track of the color, but it keeps track of it in this approximate way. And you can fairly easily convince yourself that that's almost okay if you're willing to neglect contributions that are suppressed by order 1 over number of colors squared, where number of colors is 3. So it's a 10% approximation, more or less. So with the aid of that, I can tell you a little about color coherence with what's in Pythia, which is a dipole shower. You consider that the radiating system that's going to radiate a soft gluon is made of color dipoles. And if you do it in the leading color approximation, then if I have one antiquark, one quark, and one gluon, the gluon has a green line, a color that's connected to that green line, and a red line, the color line. So that's the 3 and the 3 bar line. And we have one dipole made by the color 3 bar line here and the color 3 line there. And dipole emission tends to come between those two, concentrated at either one line or the other, but all the way in between. And there's another piece of the dipole that's between the color lines between between the gluon and this quark. That's a, say, much smaller angle. And that radiation is concentrated in the smaller angle. So if you do it that way, you get the same answer as Hurwitz does in the leading color approximation. So as long as you're doing this dipole kind of shower, you also have this coherence color. And that's something that was built into all these showers in the 90s. Okay, so I have a chance to tell you a little about how some equations for shower evolution. Here's a good way to think about it that I think you'll find helpful if you, when you hear a talk that involves parton showers, if you think about it this way. You think of statistical mechanics, and in statistical mechanics, you have a state of the system. The state vector tells the probability that the system is in some particular configuration. And if we just have momenta and flavors, then our state is inner product with PFM. That's a list of all the momenta and flavors. That's the probability that that state would be discovered to contain a lot of partons with momentum P1, P2, P2, P3, etc. And flavors up, anti-up, blue, whatever. So rho is representing a probability distribution. And the probability distribution, as the computer is always throwing dice, is changing. So we have an evolution equation for the probability distribution. The distribution at time t is equal to the distribution at time 0, the shower time, times some operator, an operator on the space of statistical mechanics space. And the form of the evolution is pretty simple. d by dt of this u that does the evolution is a certain operator that describes parton splitting, for which we have a picture here. Mother parton splits to 2. And another, which has got a minus sign in front of it, that describes no splitting. And so parton just goes along and nothing happens to it. It doesn't get to be 2 partons. It gets multiplied by something. Okay, so the splitting function comes from the QCD Feynman diagrams approximated. And the no splitting function is determined from the splitting function in such a way that the total probability that the parton state is still there remains 1. We don't change the probability. That way, if you start with a cross-section at the hardest scale, that cross-section just stays exactly the same. You rearrange where all the momentum is going as the parton shower develops. You rearrange it, but you don't change the cross-section. So if you want to conserve probability, then there has to be a relation between this b and the h. And that can, in fact, determine b. So now there's a way to write that. Here's our differential equation. d by dt of u is h minus v times u. And you've seen equations like that in quantum mechanics. And you can solve those kind of equations by writing u as nothing happens operator, the probability for not splitting between 1 time t prime and next time t, and the probability for not splitting between time t prime and an intermediate time tau, times the splitting operator of time tau, times the complete evolution operator from tau to infinity. It's just quantum mechanics perturbation theory. That's the way you organize it. For time-dependent perturbation theory, use the same formula. And then this not splitting operator is the time-ordered exponential of minus the integral of v from the one time to the other. And you call that the Sudakov factor. So everywhere inside of this shower of Montel's are Sudakov factors which are treated probabilistically. And it represents physically the probability that from the time you started to the time when the parton actually splits, it didn't split. Probability for not splitting is exponential minus the probability for splitting. Okay, so here's a picture then of what happens. Here's the complete evolution operator. Here's the probability for not splitting between 2 times. Here's the probability for not splitting up to time tau. Probability to split at time tau, and then everything else can happen. If I just take that equation and treat it perturbatively, so expand out in the number of h of splittings, then I get everything happens. Green represents here the hard scatter cross-section, so that's what you start with, and then anything happens. And then anything happening means nothing happens, or there's 1 splitting, between them nothing happens, or there's 2 splittings, nothing happens, 1 splitting, nothing happens, 1 splitting. That's the solution of this kind of equation. Again, it's familiar with perturbation theory. And just this thing, that's the way the shower evolution just works inside of the computer. You just generate splitting, you generate the probability for not splitting between any 2 times, and then the probability for the next splitting. Okay, and I should mention quantum interference. In quantum mechanics, there's interference. So this splitting function has contributions of the form amplitude to split times complex conjugate amplitude to split. And those can be different. So here's a case where the amplitude to split represented on the left of this diagram is one thing, and the amplitude to split complex conjugate is represented on the right-hand side of the diagram. It's the same thing. So here is the probability squared amplitude for a gluon to split into 2. But there's also interference that's an interference diagram. And that's in the dipole picture. Those are the diagrams you need. So now let me mention color and spin. These are quarks and gluons we're talking about. They carry color, they carry spin. They can carry color and spin a long way, over a big space-time distance, or until everything's on shell, very close to on shell. Those color and spin are quantum properties. So for the description of all of this, we need not just statistical mechanics that I was describing to you before, but quantum statistical mechanics. And you need the density matrix in color and spin space. So, to describe the spin of a photon, that is its polarization, in statistical mechanics, you want a polarization density matrix. And so you can use the density matrix also in the Parton shower Monte-Carlo. And I'm working with Zoltan Neusch on just such a thing that's it's not exact, but it does better with respect to color and spin. Okay, my last topic, which I'm basically not going to do because we're running kind of toward the end here, but I'll just mention it. You want to sometimes match showers to perturbation theory. So let me just tell you why you do that, and I'll let you know that there's a big industry to do that. In perturbation theory, you have a cross-section that you calculated, say, to make n jets, and it's alpha s to the power a in front of everything at the Born level, and then times a series of contributions with higher powers of alpha s. So at lowest order, you just have C0, and next leading order, you have C0 and C1, etc. And that will calculate for you anything that's infrared safe. But what if it's not infrared safe, what you really measure, and supposing you measure in an actual detector and the detector has little holes in it, well, sometimes they do, then actually your observable, what you really observe in the experiment, is not quite infrared safe. So it's hard to estimate then how much the cracks in the detector matter. So you'd like to put in showers, that will generate the complete event, and then you take into account how the detector actually operates. But on the other hand, why don't we just use pure showers? That's because the basis of the pure showers is approximations for the matrix elements, and those are just approximations, and you better use the complete matrix element. Okay, so that is a big industry to match Parton showers and next leading order calculations. It's not so easy, and unfortunately we just have to skip it, but I think you get the idea of the importance of it. So, what have we learned? Factorization of soft physics from hard physics enables us to make reliable predictions for experiment. The soft physics is contained in Parton distribution functions. That's at the simplest kind of level where we're not using Parton shower Monte-Carlos. Or you can extend that idea to use Parton shower Monte-Carlo mention integers. That'll give you really detailed information about the final state at a cost of accuracy. And finally, one can try to match the next leading order calculations from Parton showers, and we didn't really get much chance to discuss that. So that's it. Thanks. Any questions? If
don't know what's going on there. Something not just known as it's a supersymmetry, but something new coming in.
Yes, what you can do is simulate with this kind of a picture something that you have in your mind. However, if it's not in your mind, you can't simulate it. That's why we need a whole bunch of theorists who do understand all physics and suggest things to look for. Once they've suggested it, they can go into all these calculations. But before it's suggested, you don't know what to do. You don't know. You have no way of calculating something to look for.
I suppose I should use the microphone for the benefit of the other.
It's a question to which level that
I think you have to push
The big button.
Big button.
The big button closer to you.
to which level does this factorizing formula, for instance, for this Higgs productions in this WW boson channel were valid, and to which level, to which power, and to which order of alpha s does this factorizing?
That calculation I showed you was at next to leading order.
In the leading power.
It's in leading power, so all these factorization formulas, I didn't mention it, but are neglecting contributions of order 1 GeV divided by Q squared. Q, or 1 GeV squared divided by Q squared. So here for Higgs production, Q is the Higgs mass, so we're always neglecting anything of order 1 GeV squared divided by the Higgs mass squared. That's a tenth of a percent. There's nothing to do about that. So we're always at leading power with respect to that ratio.
So you both in the let's be order of alpha s and in leading power, as you said. So it seems that there is this SET language will have some advantage because the calendar to kind of prove the factorizations in the leading power to order of alpha s in some cases.
I'm sorry, you're saying sometimes the non-leading
If you can use this SET technique, you can just prove in the leading power the factorizing formula can work to actually order of alpha s. So compare this diagrammatic proof and these SET techniques. So then it seems that there are some special advantages of this soft commutative theory.
So what you're talking about is SCET, soft linear effective theory. That's a way of summing, rearranging perturbation theory and summing large logarithms. So if you're observable as a ratio of two momenta in it, then the perturbation theory has logarithms of that ratio, and you can sum those. And there's kind of a systematic way in SCET for doing that. Mostly, it's neglecting still power suppressed corrections.
Yes, so to order of alpha s, of course in the leading power, the power correction is also complicated in SAT. But it means you can prove it in order of alpha s. But as you said, in this case you can prove it to this NAL order.
So this Higgs production thing is just a completely infrared safe cross-section. There aren't any large logarithms to solve. So I don't think SCET is helpful there. But it's still neglecting non-leading powers. And I'm not sure if SCET can get a hold of non-leading powers. I don't think it has that in it.
Actually,
Just for these alpha s for power correction.
Yes, it does alpha S corrections. Alpha S times logarithms.
Is that the fragmentation is not really QCD based. It's kind of more like
The hybridization.
hybridization. I mean, that might violate from this factorization.
If you have an infrared safe observable, like a Chung observable, then the hybridization is happening at very long times and involves all just soft momentum exchanges. So by the design of a jet cross-section, soft momentum exchanges don't matter. So
when you talk about hot showers, actually for non-splitting part, actually you are saying is we have to put the Sudakov factor, right? For its non-splitting part.
The non-splitting part?
Yeah.
Well, I missed the last part.
You are saying is we have to put the Sudakov factor for non-splitting part.
The Sudakov.
Yeah, Sudakov.
Yes, that's what it's. The non-splitting part is just called the
So it's, in actually it's perturbative calculations, when you consider the real balloon emissions, actually we have some kind of infrared diagrams as well as for its real balloon emission diagrams. We can also have some Sudakov factor. Okay. So it's actually for non-split part, I mean, I just as guesses, I just imagined some kind of virtual fractions.
Oh yes.
Yeah.
So I didn't.
So I mean, it's with the only virtual corrections, we always have some infrared divergence. Also, when maybe as we have to combine the real balloon emission diagram and virtual corrections.
You're quite correct.
Yes.
And I didn't go into it, but
Yeah.
you have the real gluon emission, and that's going to this function I was calling H.
Yeah.
And then there's this V, and the way I said it, we just fix it by hand to conserve probability. That's because we know quantum mechanics conserves probability.
Yeah.
However, what V really represents is two things. One, emissions of gluons that are softer than the current running shower time. So soft real emissions are put into V.
Yeah.
And virtual corrections, exchanges of gluons virtually. And put those together, that's physically what that no splitting operator represents. But we just use a trick to evaluate that constantly.
Minus one question.
First, I want to make sure a split kernel is a degrad split kernel. You talk about two contributions. One is Sudakov, another is splitting contribution. The splitting is the degrad problem.
Splitting is, the splitting kernel is really more than the degrad kernel, but basically that's what it is. It's
Okay. And then, but because the Sudakov also comes from the summation of the radiations orders, so somehow these two pieces they have some double counting. So I don't know how you make sure that you don't have double counting.
As I was saying, the V operator, the no splitting operator, really corresponds to virtual emissions and unresolved real emissions. So resolved emissions count